Welcome to Lecture 3 of the Regression Analysis course. All right, in the last video, we talked about modeling in general. We have a dependent variable which we denote by y. We would have a list of independent variables that would influence the value of dependent variable in some way. And what we try to do is describe the relationship between a dependent variable y and one or more independent variables. And f over here represents that relationship between these variables. And then we have a last term, error term. If I give you a data set that contains information for an entire class of students, you have information for the exam score, which is treated as the dependent variable denoted as y. And then we have a list of independent variables. Number of hours they spent studying for the exam, denoted by x1. Exam anxiety, denoted by x2. Amount of sleep they got the night before the exam, x3. So you basically have this information. If we try to read this table, then it basically means that the observation 1 contains the information for student 1. Student 1 studied 5 hours for the exam, was anxious during the exam, and only slept for 3 hours the night before the exam and ended up scoring 90 points. Student 2 studied for 2 hours, was not anxious during the exam, and slept 6 hours the night before the exam and ended up scoring 60 points. So we have this data that contains the information of n students from a class. If we were asked to write the model equation, we have exam score as the dependent variable y, and its value is dependent. It is related to the other independent variables present in the model, which we have denoted by x1, x2, x3. Dependent variable is dependent on the other independent variables. Therefore, y, dependent variable, is a function of all the other independent variables present in the model. But here's the catch. We know that the dependent variable is dependent on all these variables. These variables are related to each other, but we have no idea how are they related. What is the exact mathematical relationship? What is the form? What is the correct form of this f? So we have no idea how this function actually looks like. And the last term we have over here is epsilon. This little guy epsilon takes care of everything we cannot capture. All the missing information, like whether the student did all the assignments, all the unobserved factors, and even the small mistakes like data entry errors. All the other things which we could not capture about, this epsilon takes care of that. Now the goal is to figure out a best estimation of f and make sure this error term is as small as possible. Now you might be wondering, what kind of functions can we use for this function fx? If I ask you all that how can these independent variables be related to this dependent variable? You could say that it might be, the dependent variable might be exponential related to all the independent variables. This fx could be a trigonometric function. It could be an absolute value function. And we have so many other choices for this function fx. We have infinite number of choices. But if I ask you to put a restriction on f, to restrict f to be smooth and continuous function, still we would have so many choices. F could be a polynomial function. It could be a trigonometric function. There are so many choices out there. But what if I ask you to put a more strict restriction on f, that is, restrict f to be linear? It is the most straightforward, interpretable, and commonly used restriction, taking f to be linear. That is, if you were to draw it, it would look like a straight line or a plane in higher dimension. Now here, beta naught, it represents the intercept, and beta 1, beta 2, beta 3, so on and so forth till beta p are the coefficients of the independent variables x1, x2, x3, so on and so forth till xp respectively. So for the same example, exam score example, if this is the data set that is provided to you, then you would write the general model equation. That is why the dependent variable exam score is a function of all the independent variables present in the model and plus some sort of uncertainty you have from each observation. This would be a general equation. Now, instead of some unknown function fx, we are assuming fx to be linear. We are taking fx1, x2, x3 is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and that's what makes it a linear model. Given this table to you, given this data set to you, you would have all the information about the dependent variable and all the independent variables present in the model. What is unknown to us are the betas present in the equation. The betas, beta naught, beta 1, beta 2, beta 3s are the unknown quantities. And these unknown quantities, we call them parameters. And now, for any given linear model, you would have information about all the variables, dependent variable and independent variable. Our goal would be to estimate the unknown quantities present in the equation using the data set given to us. So now our goal would be to estimate the value of beta naught, beta 1, beta 2, and beta 3. Well, how to estimate these parameters using the data set given to us? That is something we are going to learn future in the course. For now, our goal is linear model. So what is a linear model? A model is linear if the model parameters enter linearly in the model. The most straightforward equation we can write is, given any p independent variables in the model, the dependent variable y is a function of all those independent variables. Y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth till beta p xp plus epsilon. Let me ask you all a question. So given any random model, how would we identify that if a model is linear or not? Well, there is a mathematical way how you can find out if a model given to you is linear or not. What we do is, first we identify the parameters in the model, and then we take the derivative of the equation with respect to the parameter present in the equation. Now, if the derivative with respect to the parameter contains any function of the parameter or parameter itself, we say that the model is nonlinear in that parameter. But if it does not contain any term of parameter or a function of parameter, it is linear model. Let's try to understand it with some examples. Say you are given this model equation, y is equals to beta naught plus beta 1 log x1 plus epsilon. Now you are asked to find out if it is linear model or a non-linear model. The first step is to identify the parameters. The parameters over here are beta naught and beta 1. Once you know what the parameters are, the next thing you would do is you would find the derivative of this dependent variable y with respect to the first parameter, which is beta naught. Now remember, when you are finding the derivative with respect to the first parameter, all the other terms that do not contain that parameter would be treated as constant. So here, when you are finding the derivative with respect to beta naught, beta 1 log x1 and epsilon would be treated as constant. So when we find the derivative of y with respect to beta naught, the derivative of beta naught with respect to beta naught would be equals to 1, and the derivative of the remaining terms would be 0. Now, when we look at the derivative of y with respect to beta naught, it is 1. It does not contain any term of beta naught or beta 1 or any function of beta. So we would move to the next step, that is finding the derivative of y with respect to the next parameter we have in the equation, which is beta 1. So if you find the derivative of y with respect to beta 1, it is log x1. Again, it does not contain any term of beta. So it satisfies our condition, and we would say that y is a linear model. So you find the derivative of the equation with respect to each parameters, and if it does not contain any term of the beta, we say it's a linear model. Let's look at another example. Y is equals to beta naught plus x1 to the power beta 1 plus epsilon. The first job is to identify the parameters. Clearly, the parameters over here are beta naught and beta 1. So, first we find the derivative of the equation with respect to beta naught. Any other terms that do not contain beta naught would be treated as constant. So if we find the derivative of this equation with respect to beta naught, we get 1. And it clearly does not contain any term of beta. So we move to the next step, that is finding the derivative of the dependent variable y with respect to beta 1. Now remember, when you find the derivative with respect to beta 1, any term that do not contain, that do not have beta 1 in multiplication, that do not have beta 1 in it, would be treated as constant. So if we find the derivative of the dependent of this equation with respect to beta 1, derivative of beta naught with respect to beta 1 would be 0. Derivative of x1 to the power beta 1 with respect to beta 1 would be x1 to the power beta 1 log x1, because the derivative of a to the power x with respect to x is a to the power x log a. And if we look at the derivative of y with respect to beta 1, it contains a function of beta 1. It contains a term of beta 1. And this makes it a non-linear model. Let's look at another example very quickly. Say you have an equation, a model, y is equals to beta naught times x1 to the power beta 1 plus epsilon. And if you have to find out if it is a linear model or non-linear model, as usual, first step, to identify the parameters beta naught and beta 1. And now you will find the derivative with respect to the first parameter present in the equation, which is beta naught. So if we find the derivative of this equation with respect to beta naught, we would have x1 to the power beta 1. And it clearly contains a function of beta 1. So you would just stop here. You don't have to find the derivative of this equation with respect to beta 1, because clearly when you are finding the derivative of this equation with respect to the first derivative, it contains a function of beta 1. So you stop here and you say that this model is a non-linear model. But here's the thing. This is a non-linear model, but you can transform it into a linear model. How can we do it? Try taking log both sides over here. If you take log both sides, you would have log of y is equals to, you use the multiplicative property of logarithm function, which is log of a times b is equals to log of a plus log of b. So you get log of beta naught plus log of x1 to the power beta 1. And now we use the power rule of the logarithm function. So here we can further simplify it, and we have a term log x1 to the power beta 1 and beta 1 using the power rule property of the logarithm function, which would make it beta 1 times log of x1. So now we have reduced our equation to log of y is equals to log beta naught plus beta 1 times log x1. Once we have simplified it, now we look at both the terms. So the first term is log beta naught and the second term is beta 1 log x1. So the term that do not have any term of x in multiplication or division, we rewrite it as another constant c naught. Now remember, the c naught is just a notation. So if you have a parameter, while simplifying it, you get a function of that parameter, and if it does not have any term of x in multiplication or division with it, then you can again give it another notation c. But remember, you cannot do it with any other parameter that has x1 in multiplication with it, or any independent variable in multiplication or division with it. Hypothetically speaking, if you had log beta 1, you cannot write it as another parameter. You can only do it with the parameter that do not has any term of x in multiplication with it. So we had nonlinear model, we took log both sides, simplified it, and further wrote a function of the parameter that do not have any term of independent variable in multiplication or division with it as another constant c naught. So now our new parameters over here are c naught, which is a function of beta naught, and beta 1. So, to find out if this new transformed equation is linear or not, you take the derivative of this log y with respect to c naught and the derivative of this log y with respect to beta 1. Clearly, if you take the derivative of this new transformed equation log y with respect to c naught or beta 1, it will not contain any term of c naught and beta 1 in it. Thus, we have log of y as a linear model. So here's the conclusion. A model could be linear or non-linear. If the model parameters enter linearly in the model, you would say it's linear. However, if the model is nonlinear, sometimes using an appropriate transformation can convert a nonlinear model into a linear model. And that's it for this video. I hope the concept of linear model and non-linear model is clear to you all, and I'm going to see you all in the next video.